First, I would like to thank the organizing committee of the 2017 Eurochem conference for inviting me to give a keynote presentation. I am RanjanSiriwardane with United States Department of Energy in National Energy Technology Lab in Morgantown, West Virginia. Today I'm going to discuss the chemical looping combustion and gasification technologies for production of heat and valuable commodities. Now, chemical looping combustion is a novel combustion technology that uses oxygen from an oxygen carrier, such as metal oxide, for combustion of fuel instead of using air. The process involves two reactors, fuel reactor and the air reactor. In the fuel reactor, the fuel, methane or coal react with the oxygen carrier metal oxide to produce carbon dioxide and water. Now, if you condense water, you get a pure stream of carbon dioxide. This is a big advantage because we don't have to separate nitrogen from CO2 as we get in the air combustion with fuel. After the reduction in the fuel reactor, the reduced metal is transported to the air reactor. Then the air is introduced for oxidation, and heat is generated from this reaction, which can be used for many applications. And so the pure stream of CO2 here, produced here in the fuel reactor, is ready for sequestration without any additional cost for separations. Also, there are reduced NOx problems in this particular process. And the reaction in the fuel reactor is generally endothermic except for copper oxide. And so some of the heat produced here has to be transferred to the fuel reaction. Now, oxygen carrier development is very critical for the chemical looping combustion process. There are many challenges. It has to have high oxygen transfer capacity, as also high reaction rates, high attrition resistance, stable performance during multi-cycle test at high temperature. There's reduction, oxidation takes place at a high temperature, and there should be no agglomeration, and also scaling up the manufacturing process. Now, pure metal oxides and supported metal oxide have been previously investigated, and they are reported in the literature. The most common oxides that have been used are iron oxide, copper oxide, nickel oxide, and manganese oxide. Now, iron oxide and manganese oxide, they're inexpensive, but they have low reactivity. Now, copper oxide, it has high reactivity, and also the reaction is exothermic with the fuel, which is a big advantage because you don't have to carry heat from the air reactor to the fuel reactor when you use copper oxide. However, the melting point of copper oxide is low, so there are agglomeration issues due to its low melting point. Now, nickel oxide has high reactivity, but there are environmental issues. It is a suspected carcinogen. At NETL, we have conducted research with mixed metal oxides to overcome some of the difficulties or the issues with the single metal oxides. We have studied copper oxide, iron oxide containing bimetallic oxygen carrier, and we have done a lot of work with this oxygen carrier. And recently we have been looking at trimetallic oxygen carrier containing copper oxide, iron oxide, and manganese oxide. Now, when we prepare the materials, these oxygen carriers in the lab, we do the initial evaluation to test the reactivity using thermogravimetric analysis, or TGA. Now, we can use milligram level quantities for this technique. We place the solid in the TGA pan and then heat the solid in the to the reaction temperature, and then we introduce the fuel gas methane for the isothermal reduction at the reaction temperature, and then we use air for the oxidation. We monitor the mass change as a function of time during these reactions, and using that data, we can compute the oxygen transfer capacity and also the fractional reduction. And using that, we can also compute the global reaction rates data. The other technique we use for the initial evaluation is differential scanning calorimetry combined with thermogravimetric analysis. Now, for this test, we place the solid material in the reaction pan and introduce methane at ambient temperature. Then we do a temperature ramp from ambient to 1000 degrees C in methane. And we do simultaneous differential scanning calorimetry, DSC, and thermogravimetric analysis during the temperature ramp in methane. Using the TGA data, we can identify the reaction initiation temperature as well as global reaction rates. And then with the DSC, we can identify the exothermic and endothermic reactions during the ramp. As I mentioned earlier, we have done a lot of work with the copper oxide, iron oxide, bimetallic oxygen carrier. These are some of the initial data with the DSC TGA. We use methane as the fuel and air for oxidation. Here's the weight loss data during the temperature ramp with copper iron oxygen carrier. For comparison, I also included the data with the single metal oxides, iron oxide and copper oxide. As you can see here with this bimetallic copper iron, the reaction initiates at a lower temperature with methane, as seen by the weight loss initiates at a lower temperature here. And so this indicates that there's some synergetic effects by having the copper and iron together. Actually, the copper enhances the deeper reduction of iron. And this reaction is, these are the heat flow data during the ramp. The reaction is exothermic, very similar to the copper oxide, and it's different from the iron oxide, which has endothermic reaction. Okay, this is again an added advantage because with the copper iron, we don't have to transfer heat from the oxidizer to the fuel reactor. Okay, these are the TGA multi-cycle test data with methane in air at 800 degrees C. The weight losses we see during the methane introduction is due to the oxygen loss from the metal oxide, and the weight gain is due to the oxygen uptake during the introduction with air. So we conducted 50 cycle test and at 800 degrees C. As you can see, initially there's an activation period, and after that the performance is very stable. And the material also has very high oxygen transfer capacity. So since we saw promising results with our lab scale preparations, we worked with an industrial partner, Nexerus, to prepare 500-pound batches of this material. We added alumina to the copper iron to enhance the strength of the material to get better attrition resistance. We prepared samples with two different particle sizes, spray dried material to get 50 to 250 micron particles, and also the tumbling method, that's pretty much wet agglomeration method, to produce 170 to 82 micron particle sizes. And then we conducted both bench scale test and pilot scale methane CLC test with these materials. Okay, the initial reaction performance evaluation was done using in our bench scale fluidized bed reactor. We use about 25.4 centimeter bed height, and we introduce methane for reduction and then air for oxidation, and we conducted a 25 cycle test, and we measured the effluent gas stream using a mass spectrometer. And then using the data, we computed the percentage of methane conversion to CO2. The other important parameter that we measured is the attrition resistance. The material has to move from the air reactor to the fuel reactor back and forth. So it has to have high physical strength. So we use the ASTM method to measure the attrition resistance of this material. The method the unit has 3 air jets, and we introduce air to the material at a very high flow rate, and we conduct the test for 5 hours, and we collect the fines during the 5 hours. Attrition index is defined as the total fines collected divided by the initial mass. So if we get a low attrition index, that means the material has high physical strength. So we measure the attrition resistance of the fresh material and also of the 25 cycle methane and air CLC test. These are some of the fluid bed reactor data at 800 degrees C with methane and air, and also some attrition data. Okay, we did test both particle sizes. As you can see, the methane conversion was pretty much very stable during the 25 cycle test with both these particle sizes when we conducted the test in the fluid bed. Okay, so we can see stable reactivity, and these are the attrition test data. And usually we compare the attrition resistance with the standard material that we use in the fluid beds. As you can see, both these copper and oxygen carriers had a lower attrition index than the standard materials. So that means the attrition resistance of copper and commercial preparations were suitable for the pilot scale test. So we tested this material, copper and alumina oxygen carrier, in our 50 kilowatt thermal integrated chemical looping reactor. And the fuel reactor here is a bubbling fluidized bed. We introduced methane here. And after that, it's transported to the air reactor using an air valve. And the air reactor, we introduce air, and it's transferred through the riser to the cyclone and back to the fuel reactor. And the air reactor is a turbulent fluidized bed. And so some of the key design parameters, there's no external heat added to the solid paths. So self-sustaining operation is possible if heat released is equal to the heat loss. So this is a summary of the 50 kilowatt thermal scale test with the copper, iron, alumina oxygen carriers. We saw easier operation and less solid losses with the bigger particles, that's 177 to 500 micron, than that with the smaller particles for this current system design. Now, we achieved more than 40 hours of chemical looping combustion operation. That means we can get autothermal operation without adding external heat to the process. And for this size pilot scale unit, this was possible because of the exothermic reaction in the fuel reactor. We didn't have to carry heat. And we didn't see any agglomeration of the particles. We operated up to 950 C, and even though the copper concentration was 38%, which is very high. We saw good solid circulation, methane conversion, and good heat management. And we did see some solid losses, so our next goal is to improve the attrition resistance of the material further. We have been also looking at cold chemical looping combustion with the copper, iron, alumina oxygen carrier. We did some bench scale fluidized bed test to test the coal CLC. And here we mix coal with the oxygen carrier and placed it in the reactor, and then did a temperature ramp from ambient to 850 C in argon in the fluid bed reactor. And we added 30% steam during the temperature ramp, and we measured the effluent gas composition using a mass spectrometer. Okay, these are some of the data, the fluid bed CLC data with Wyodak coal and Illinois coal using copper iron oxygen carrier. The coal chemical looping combustion that involves several reactions. The coal reacts with steam to produce carbon monoxide and hydrogen, and then the syngas, the CO and hydrogen, reacts with the metal oxide oxygen carrier to produce carbon dioxide and water. In addition to that, the metal oxide, when you heat up the metal oxide, it can also produce oxygen, and that oxygen can react with coal to produce carbon dioxide. These are the CO2 concentration data during the temperature ramp. For comparison, I also included the data with the coal and the steam without the oxygen carrier. And these are the data for Wyodak coal, which is a sub-bituminous coal. And these are for the Illinois number 6 coal, which is a higher rank bituminous coal. As you can see, when the oxygen carrier is present, the CO2 production rate is significantly higher than that with the blank coal. So this indicates that the oxygen carrier enhances the CO2 production, and also the amount of CO2 produced is significantly higher when the oxygen carrier is present. And so the oxygen carrier promotes the coal gasification process and also the subsequent combustion process. So we saw similar behavior with the Illinois number 6, but the rate enhancement was more significant with the Wyodak coal. Okay, recently we have been also looking at the trimetallic oxygen carriers. We looked at copper, iron, manganese oxygen carrier. And these are some of the TGA DAC data during temperature ramps. You can see the weight change as a function of temperature. Now again, for comparison, I also included the single metal oxide data. As you can see, when the methane was introduced to copper, iron, manganese, and when we conducted the temperature ramp, the reaction starts at a lower temperature with the trimetallic as compared to the corresponding single metal oxides. We saw similar behavior with when we compared with the bimetallics. Again, the trimetallic initiates the reaction with methane at a lower temperature. So this again indicates there's a synergetic effects due to having the three metals together, and the copper seems to again enhance the deeper reduction of iron and manganese. And we saw better reactivity and oxygen capacity due to these synergetic effects. So summary of the chemical loop in combustion, mixed metal oxide oxygen carriers showed better reactivity and stability, and the commercially prepared copper, iron, aluminum oxygen carrier showed very promising results during the test in our 50 kilowatt thermal pilot scale unit. And we saw better results with the bigger particles. The trimetallic copper and manganese also showed better performance than the corresponding single bimetallic oxides. We saw promising results with bench scale coal chemical loop in combustion with the copper, iron, aluminum oxygen carrier. And for future work, we would like to improve the attrition resistance and lower the cost and do more tests with coal. Now, we have been also looking at chemical looping processes to produce valuable commodities. Now, syngas, which is a mixture of carbon monoxide and hydrogen, and also hydrogen, they are the precursors for many of the products that we use every day. So we are looking at $1 billion product market with these materials as precursors. Now, commercial preparations of syngas and hydrogen, they're done using coal and natural gas. And we are now looking at chemical looping processes to produce syngas and hydrogen from natural gas and coal. The first process we have been working on is the production of hydrogen and carbon or syngas via catalytic methane decomposition. Now here we use copper, iron, aluminum oxygen carrier. Now it has a dual function. The oxygen carrier is used for chemical looping combustion, as I described earlier, to produce heat for the process, and the reduced oxygen carrier acts as a catalyst for methane decomposition. So the reduced copper iron oxygen carrier decomposes natural gas to hydrogen and carbon, as shown in this equation. And carbon is also a useful product, so we can stop here. Or if you want syngas, you can introduce steam for the carbon gasification to produce syngas as shown here in this equation. Now this methane decomposition reaction is an endothermic reaction, so it requires heat, and we can use the chemical looping combustion process with the copper and alumina to produce heat for the process. So we are looking at the three reactor systems. In the catalytic reactor, the reduced oxygen carrier, copper and oxygen carrier, reacts with natural gas to produce hydrogen and carbon. Then in the fuel reactor, the natural gas reacts with the copper and oxygen carrier in the oxidized form to produce concentrated gas stream of carbon dioxide. It's ready for sequestration or any other application. And the reduced oxygen carrier is transported to the air reactor, and the air oxidation generates heat that can be used for the methane decomposition reaction. We have conducted bin scale test at 800 degrees C to evaluate this process of methane decomposition. Here in the initial stages, the oxygen carrier reacts with methane to produce CO2 and water. In the stage 2, when methane is introduced to the reduced oxygen carrier, it produces carbon and hydrogen. These are the hydrogen production data. During stage 2, you can see we get a very high conversion of methane to hydrogen at 800 degrees C. It's higher than that at 700 degrees C. And during cyclic operation, we get very stable performance as well. Then after that, we introduce steam to gasify the carbon that's produced from the methane decomposition to produce syngas. And these are the syngas production data in stage 3. And the hydrogen to carbon ratio of 2 is seen in the cyclic test, and that's very useful because we can use that for the downstream chemical processes, and we get very stable performance. The other process we have been looking at is the chemical looping gasification using oxygen carriers to produce syngas from coal. This process also has two reactors, the fuel reactor or the reducer or the gasifier. The coal is gasified using oxygen from the metal oxide oxygen carrier. And in the presence of steam, it produces syngas, carbon monoxide, and hydrogen. And the syngas does not contain nitrogen because we are not using air. So this is a big advantage that we don't need an expensive air separation unit to produce oxygen for the coal gasification process to produce syngas free of nitrogen. And this concentrated stream can be used for chemical production. Now after the reduction, the reduced oxygen carrier is transferred to the oxidizer. The air is introduced, and this oxidation reaction is exothermic, generates heat, and that can be used for the reduction or the gasification process. But however, this process is very challenging. It's very difficult to find the right oxygen carrier for the process. If you look at the reactions in the gasifier, all the desirable reactions should produce syngas. So these include solid-solid reaction, steam gasification, water gas shift reaction, CO2 gasification, and water splitting reaction. They all produce carbon monoxide and hydrogen. The undesirable reactions, they consume the syngas by oxidation. For example, metal oxides that we use for the oxygen carriers, they can react with carbon monoxide to produce CO2 or react with hydrogen to form water. Unfortunately, most of the metal oxide oxygen carriers participate in the reaction, and it's very difficult to control the reaction at the syngas stage. So we have developed here at NETL some novel materials for the chemical looping gasification. These are group 2 ferrites. These are calcium and barium ferrites. And now they have unique properties. They can react with coal to produce syngas, but they do not react with syngas to produce CO2 and water. So we can control the reaction at the syngas stage. Okay, we conducted bench scale fixed bed flow reactor test to evaluate this concept. Here we mix coal with the oxygen carriers, this is calcium ferrite, and placed it in the reactor, and we did temperature ramp from ambient to 850 C in helium. And in some tests we also added steam during the temperature ramp, and we measured the reactor effluent gas concentrations using mass spectrometer. Okay, these are the gas compositions when we had calcium ferrite, coal, and when we did the temperature ramp, and this is without steam. As you can see, the CO is the main product that's formed during the ramp. So the calcium ferrite reacts with coal to produce mainly carbon monoxide. And when we did the temperature ramp in the presence of steam, the main product was hydrogen. So the steam enhances the hydrogen production. So then we did some reaction modeling. So we took various reaction models that are in the literature and investigated these models to describe the TGA data. Now, from the analysis, we found that the Cha conversion using the metal calcium ferrite proceeds via 3 parallel processes as shown here in this graph. The carbon monoxide and CO2 formation. Initially, they followed the first order reaction model, while the shrinking co-model diffusion is responsible for the carbon monoxide production later. So the reaction is shown here. From using the data, we can get this reaction progress here. Initially, it's the metal oxide oxygen carrier. The surface reacts with the Cha to produce carbon monoxide and CO2, and then the oxygen in the bark transfers through the reduced oxygen carrier layer to react with the coal Cha to produce carbon monoxide. So later in the reaction, the carbon monoxide is the main product. So this controlled diffusion of oxygen through the oxygen carrier is the reason why we are getting more carbon monoxide than CO2. So the summary of the chemical looping processes to produce valuable commodities. Now, production of hydrogen and carbon or syngas can be achieved via catalytic methane decomposition combined with heat from the chemical looping combustion using the copper iron metal oxide oxygen carrier. And also the calcium and barium ferrite, they showed promising results for chemical looping coal gasification. They react with the coal but not with syngas, so we can produce syngas from the reaction. Thank you for your attention, and please contact me if you have any questions or if you need any additional information.